Welcome to the quantum world, where the rules are completely different from the world we see around us. Imagine you are playing a video game with two cheat codes. These are superposition and entanglement. First, superposition. In the normal world, a coin is either heads or tails. But in the quantum world, a particle is like a spinning coin. When it's spinning, it is both heads and tails at the same time. It doesn't choose one until you look at it. That's superposition, being in multiple states at once. Second, entanglement. Imagine I have two magical dice. If I roll one in Malaysia and it lands on a 1, the other dice, even if it's on the moon, instantly also shows a 1. They are mysteriously linked, no matter the distance. They share the same fate. We call this spooky action at a distance. Now, let's use these cheat codes for quantum teleportation. Here shows a blue dot, which is the secret, a green dot, which is the messenger, and a red dot, which is the receiver. The green and red dots are entangled, linked by a glowing string, even though the red dot is far away, but they are still connected. We don't scan the blue particle to copy it physically. Instead, we use the green particle as a messenger. We send a regular phone call, which is a classical info, to the red dot. The red dot uses this info to change its state. The blue dot's identity, which is quantum state, has been transferred to the red dot. The original blue dot is no longer blue. This isn't Star Trek beaming you up. It's teleporting the information, not the matter itself.
Still don't get it? Fine, let's break it down. Superposition means a particle can behave as both wave or particle at the same time. This concept applies to qubits. In classical bits, the number can only be either 0 or 1. However, in qubits, it can be 0 or 1 or superposition of 0 and 1 until measured. Superposition is what we call a quantum state. Quantum entanglement is also one of the concepts used while discussing about quantum teleportation, which refers to when two particles become entangled, their quantum states become fundamentally linked. No matter how far they are from each other, the measuring state of A will determine the outcomes of particle B. Now, an interesting one, the no cloning theorem. In classical physics, we can copy data easily, while in quantum physics, to make a copy of quantum state, the original state must be destroyed. So, combining these three concepts, we can finally understand the concept of quantum teleportation and information transfer.
Although quantum teleportation doesn't transport matter, it allows quantum information to be transferred securely and accurately. This capability has made it one of the most promising technologies for the future of communication and computing. One of the most important applications of quantum teleportation is quantum communication. Scientists can transfer quantum information between particles without physically moving the particles themselves. This technology could make future communication systems significantly more secure. Any attempt to intercept or measure the transmitted quantum information would immediately disturb its quantum state, making eavesdropping indetectable. Quantum teleportation also plays an important role in quantum computing. Quantum computers use quantum bits, or qubits, to perform calculations that would be difficult for classical computers. By teleporting quantum states between qubits, information can be transferred efficiently within quantum computing systems without directly moving the physical particles themselves. Researchers are also developing the concept of quantum internet, where quantum teleportation could enable highly secure communication between distant quantum devices. Despite its enormous potential, quantum teleportation faces several limitations. First, it requires quantum entanglement, which is extremely fragile and difficult to maintain over long distances. Quantum teleportation also cannot transmit information faster than the speed of light. Although entanglement occurs instantaneously, classical communication is still required to complete the teleportation process. And lastly, building quantum communication systems require highly specialized equipment and extremely controlled environments. Quantum states are easily disturbed by their surroundings, causing errors during transmission.